speaker, that is Stefano Martina. Are you here, Stefano?
Yes, can you hear me?
Yes.
Okay.
So, a brief introduction. Stefano is a postdoc at the physics department of University of Florence. He's working on quantum machine learning, and this talk is about benchmarking quantum noise via machine learning. Please, Stefano, go ahead. You have 25 minutes as well.
Okay, thank you very much. We'll introduce you on our work on machine learning methods to classify quantum noise. And I will start with an introduction, followed by a definition of the problem, and an introduction to the machine learning methods that I used in our experiments, and finally the results of our experiments. So we consider a quantum random walker on a complex graph of quantum states that form a computational basis, and we simulated an open quantum dynamics for the walker that is perturbed by a noise. We want to discriminate the kind of used noise by measuring only the population of the walker inside of the nodes of the graph. And we employ a classical machine learning algorithm that is subprofector machines, and a more recent deep learning technique that is recurrent neural networks. We found that the parameters that we use to simulate the dynamics are crucial to the capability of the machine learning model to classify the noise. If we use a short evolution time with a high sampling frequency, the problem is easy to classify. And if we use a long evolution time with a low sampling frequency, the problem is harder. Overall, we obtain more than 90% of accuracy in the classification between the two different noises that have same support but different sampling distribution. The two noises can be both independent and identically distributed, and that means that the process is Markovian, and the distribution used to sample the noise does not depend on time. The two noises can be also both colored, and that means that the process is non-Markovian, and the distribution used to sample the noise depends on time. And also one noise can be IID and the other one colored. We found that when we use two colored noise, the problem is harder respect to the other two. So to enter more in detail, we generate 40 different states that are depicted as the colored circles in the figure, and two different kind of noises that can be IID or colored. And we generate a random configuration of the states that are the edges between the nodes, and we choose a random node where the population is totally initialized. Then we evolve the dynamic in two different ways, depending on which one of the noise we use to perturb the dynamic. And we sample 15 evolution steps, and we keep also the information on which one of the label of the noise was used to perturb the dynamic. Then we repeat the process with different random configurations and different random initial states to generate 10,000 different samples to train a machine learning method to classify which one of the two different noise was used to perturb the dynamic. We generate different settings. On the left, you can see an example of the population, a part of the population of the nodes, where the total dynamic time was set to 0.1 natural units. This is the sufficient time for the walker to escape the initial state. On the right part, you can see an example of the population where the total evolution time was set equal to 1, and in that case, the node population escape from the initial states and also return many times, diffuse and return. And in these settings, the information is more fragmented and the classification process is more difficult. So now we talk about the machine learning methods, and in general we can formalize a machine learning method as a nonlinear function that is parameterized with parameter theta that are modified during the training, and hyperparameters xi that are fixed during the training and are used to change the different model configurations. During the learning process, in theory, we would like to optimize, to minimize a theoretical risk function that is the expected value of a distance called loss between the output of the model and the desired output y. But in general, the distribution that generates the data is not known, and we have only a set of data points. And we can use the set of data points to minimize an empirical risk function that is the average of the loss. In general, we don't use all the available data to train the model, but we keep part of the data as a validation set to check how the model is capable to generalize to unseen data, and also to tune the different hyperparameters of the model. And also we keep another part of the data to calculate the metrics and report the results. Subprofector machine is an evolution of the maximal margin classifier, and the training consists in finding an hyperplane that separates the data points in the two classes. If the data is not linearly separable, for instance, because it's mixed, subprofector machines have two techniques to deal with that situation. One is to allow for some data point to be in the opposite part of the separating plane. And the other one is to increase the dimensionality of the data in such a way that in the new space, the data becomes linearly separable. Artificial neural networks are composed of artificial neurons that performs a weighted average of the inputs plus a bias and apply a nonlinear function that usually is a sigmoid, an hyperbolic tangent, or a rectifier. Artificial neurons are organized in the feed-forward neural networks in layers, where each layer process the output of the previous layer, and the output of the layer is given in input to the next one. The output of the last layer is also the output of the network. The parameters of the artificial neural networks are the weights of the single artificial neurons, and the hyperparameters are, for instance, the number of neurons per layer and the number of layers. In classification problems, the common used loss is the categorical cross entropy. And in order to use that loss, the output of the model needs to be in the form of a probability distribution. And we can obtain that normalizing the output of the multi-layer perceptron with the softmax function. The general algorithm that is used to train artificial neural network is the backpropagation with stochastic gradient descent. First, we provide an input to the neural network and we obtain an output. Then we calculate an error with the loss and we backpropagate the error in the network to calculate the gradients of that error surface in the space of the parameters of the network. Then we perform a step in the opposite direction of the gradient. The length of the steps is controlled by the learning rate eta that can also be adaptively updated during the training using methods like, for instance, Adam that we use in our experiment. Also, we don't use all the training data set to perform the gradient descent, the descent step, but we iteratively use small parts of it that we call mini batches. Recurrent neural network are artificial neural network specialized on the processing of sequential data, and they are basically constituted by a nonlinear function that updates hidden state h with the input at a certain time. And the hidden state is like a sort of memory of the network. To perform the classification, we take the final state of the network and we use that as a representation of the entire sequence, and we perform the classification with a layer of a neural network. If we implement the recurrent function with a single neural network layer, we have the problem of vanishing gradient. The initial inputs of long sequence don't have an effect on the final state. To avoid that, we can use a long short-term memory or a gated recurrent unit that both adopt a mechanism of learned gates to control when and how update the hidden state. Recurrent neural network can be extended both in depth, like in multilayer perceptron, and also in direction. This is the same recurrent neural network of the previous figure. And this one is a specular recurrent neural network that processes the inputs in the opposite direction, starting from the last one to the first one. The output, the hidden states of the recurrent neural network are processed by other recurrent layer that takes the states of the previous layer as input. The final hidden states are then aggregated in some way, and the classification is performed by a final neural network layer. The aggregation can be similar to the one that we saw in the first example, where we take the final hidden state of the recurrent neural network, both the final of the forward and the final of the backward part, and we use that to perform the classification. We concatenate them and we use them to perform the classification. Using the max pooling aggregation, we have that each element of the tensor is obtained with a temporal max over all the hidden states of the last recurrent layer. And the attention mechanisms perform a weighted average of all the hidden layer of the last hidden representation of the last layer of the recurrent neural network, where the weights of the average are learned with are obtained with a learned mechanism. So to conclude, we have that we generate two different settings for our data. One with a short a short length for the Walker dynamic of 0.1, and one with a longer temporal length for the Walker. And for each one of those two settings, we generate three different data sets. One with two different IID noises, one with two different colored noises, and one with one IID versus a colored noise. And for each one of those data sets, we train two models that read as input only the last population at the final time. And SVM, one is an SVM and the other one is a multilayer perceptron. And we trained also several models that read all the population after each step of the quantum dynamic. And SVM is a supervector machine that that has an input the concatenated population. GRU and LSTM are unidirectional deep recurrent neural network that has a process as input the population and use GRU unit or LSTM units. By GRU and by LSTM are bidirectional deep recurrent neural network. By GRU ATT and by LSTM ATT are bidirectional recurrent neural network that use an attention mechanism instead of the standard aggregation. And finally, by GRU max and by LSTM max uses max pooling aggregation. First, we notice that when we use the short dynamics, already the models that read the final population are good to classify between the two different noises. In case of IID noises and IID versus colored. For the two colored noise, we need to adopt recurrent neural networks to obtain more than 90% of accuracy. And then if we look at the longer dynamic, we see that the final population is not sufficient to train the models. In fact, they have a 50% of accuracy and they do basically random guess. And we need to adopt a recurrent neural network on all the populations. Also in that case, we see that the problem to classify two different colored noises is more difficult respect to the other two. And other remarks are that SVM performs worst respect to the deep learning methods. The bidirectional recurrent neural networks perform better respect the unidirectional recurrent neural networks. Also, GRU perform better respect LSTM. And finally, the max pooling perform better respect the attention mechanism and the standard aggregation. We are in the process of submitting a paper written by me, Stefano Gherardini, and Filippo Caruso, and we are also planning to apply those results to real data. We have many open postdoc positions on quantum machine learning, quantum sensing, and more in general, quantum information theory in our group. And if you are interested, please contact Professor Filippo Caruso at that address. Thank you very much. If you have a question, feel free to ask.
Hi, Stefano. Thank you for the very interesting talk. So we have a couple of questions from the audience. Okay, there is one saying, which is preferred LSTM or GRU? But
probably this was asked before the last slide. In this setting, I found that GRU perform a bit better respect to LSTM.
And what could be the reason for different type of noises?
The reason, well, in that work, we generate different type of noises. This can be, sorry, this can be applied to real data, because we don't know in reality what is the kind of noise that can happen in quantum dynamics, and we can, for instance, train those models with different kind of noises and try to use on real data to classify which one is more similar to the real noise.
Okay.
In this setting, we generate the noise. We choose two different kind of noise, and we train the model to classify between the two kind of noises.
Okay, thank you. Maybe another question. Have you considered convolutional neural network and or geometric deep learning?
No, we didn't try convolutional neural networks. The data was intrinsically sequential, so we think about applying recurrent neural networks.
Okay, maybe I have just one last question. For what concerns the SVM, did you try so as you said, SVM gives you the possibility to map the problem into higher order dimensional spaces. Did you try different kernels for doing that?
All the models, also deep learning models, were optimized on hyperparameters. On SVM, we tried linear kernels, quadratic, cubic, and RBF kernels. And also the deep learning models were optimized on different configuration, the different numbers of layers and different dimension of layers.
Okay. For the kernels, have you seen which one works better for, or not a rule, general rule?
The better here, I think, are RBF.
Okay.
But I perform the experiment with all, and I take the higher value in validation set.
Maybe, we have time for one other question from Enrico.
Okay, well, thank you for your excellent talk. I have a question about the very beginning of your talk, because I would like to ask you some more details about time correlation of the noise. So can you please say some few words more about what kind of time correlation you expect to detect? And because that is related to the use of the recurrent part of the neural network. Can you say something in comment?
So basically, in this case, we generated the noise. So when I talk about IID noise, basically the probability distribution is always the same for every one of the 15 samples of the dynamic. Well, if you go to this scheme, we have the green plates. Basically means that the dynamic is repeated for 15 temporal steps. And in each one of those 15 steps, we sample a value of the noise from the same distribution. And if we use colored noise, that distribution changes over time and changes with a process. So the difference is because is that in the first case the distribution is always the same for all the time steps. In the second case, the change depends on the steps based on the previous distribution also.
Okay, thank you so much for clarification. Thank you so much.
You're welcome. Thank you very much.
So, thank you, Stefano. I think you can stop sharing your presentation now.
Okay.
And we can go on with our next speaker.
Okay. Thank you. Bye.
Bye. Bye.